Let's now finish by considering the last Kaldor fact. Among the fast-growing countries of the world, there's an appreciable variation in the rate of growth of the order of 2 to 5%. So this is first half of the 20th century. However, we've seen that still today there are wide discrepancies between growth of GDP and growth of GDP per capita between different countries. Unfortunately, these discrepancies are not explained within the context of the Soros-1 model, simply because here we take them as exogenous, so we're not saying where these differences in G and N may come from. Understanding why some countries have a very fast growth in technology while others do not is a huge challenge and may probably have many explanations and is an ongoing area of research in economics. Understanding variations in population growth rate is somewhat easier, and as we're going to see later in the class, so we get a good idea why this is the case. Now, one important prediction of the model, though, is that if two countries have similar levels of growth rate of technology G and of population N, then their growth rates in terms of capital and in terms of output should be similar. So this is what we're going to consider next. So consider this convergence in terms of growth rate. So this is the final version of the Soros-1 model augmented with technology. It looks pretty much like all the other versions. There's one crucial thing that did change is that now we consider everything in terms of per effective worker. So we know that since technology always grows, then we have to include the fact that so capital and output would always grow. And but they're going to reach a steady state in terms of per effective worker. So capital should, in the long run, converge to this level K tilde star of capital per effective worker. Output should, in the long run, converge to this level of output per effective worker, consumption per effective worker, and investment per effective worker. So everything looks the same, it's just that we have changed the denominator, basically. All right, so now we're going to generate some expression for per capita growth, GDP per capita. So don't worry, we're going to have lots of algebra, but you know you can go back and look at it in your own time, and it's not that complicated. So here, let us assume the simplest version of production function we can have. So a Cobb-Douglas. So the production is f of k al equals to k to the alpha al to the 1 minus alpha, where alpha is between 0 and 1. Typically, alpha is around 0.3 because that's the importance of capital in the production function. So let's go ahead and divide by effective worker AL, so that we may get this familiar version. And note that if we divide AL to the 1 minus alpha by AL, then we get simply AL to the minus alpha. So it goes here at the denominator. So this K to the divided by AL is simply K tilde. So we get that f of K tilde is equal to K tilde to the alpha. So it's a very convenient form of function to work with. So let's go ahead and write down our law of motion of capital. Delta K tilde T is going to be investment in time T, so S multiplied by output in time T, so K tilde to the alpha at time T, minus here we have a big dilution effect, so we have depreciation plus growth rate of technology plus growth rate of population that multiplies k tilde t. Now, what we're going to want to do is find an expression of GDP per capita growth without savings. So to do that, let's substitute savings with an expression of k tilde at the steady state. So to do that, we know that delta k tilde star at the steady state is 0. So then we can write down our expression. So S of k tilde star to alpha equals to delta plus g plus n k tilde star. So here it's convenient. We have k here and k here. So let's just divide by k tilde star to the alpha. So we get this expression for S equal delta plus g plus n k to tilde star to the 1 minus alpha. And we can use that to substitute back in the law of motion of capital. And here, let's just define explicitly what delta kt is. So it's kt plus 1 minus kt. And it's equal to the same expression as here. It's just that we have substituted s here. So this is, it looks like a mess, but we can obtain a simpler expression. Actually, what we're going to isolate is k tilde t plus 1. So here it is, k tilde t plus 1 equals to 1 plus delta plus g plus n multiplied by k star divided by k tilde star divided by k tilde t to the 1 minus alpha minus 1. That multiplies, the whole thing multiplies k tilde t. So right away, what can we see? Well, imagine that k tilde t equals to k tilde star. So if capital is, the capital per effective worker is at its steady state value, so we're in the long run, this is 1, so we get 1 minus 1. And what do we see? We see that k tilde t plus 1 equals to k tilde t, so there is no growth in k tilde, which is what we want at the steady state, so on the balanced growth path. However, so all right, so what we are going to do now is consider not, so capital is interesting, but we care about GDP per capita. So let's write our expression for the growth rate of GDP per effective worker. It's G of y tilde t equals to y tilde t plus 1 minus y tilde t divided by y tilde t. And then we can substitute all of these by their expression in terms of k. So this is k tilde t plus 1 to the alpha. This is k tilde t to the alpha, and the same at the denominator. And then this thing is expressed in terms of k tilde t. So I'm going to be able basically to substitute this here and then cancel the k tilde t to the alpha everywhere and get a much simpler version, much simpler expression for g of y tilde t. After much simplification, we get this expression for the growth rate of output per effective worker. So one thing to note is that here we had a ratio of capitals. What happened? Well, simply we use the fact that output is the capital to the alpha, so the ratio of output is going to be the ratio of capital. The ratio of capital is going to be the ratio of outputs to the 1 over alpha. We're not interested in the growth rate of output per effective worker because, again, we don't really know what technology, how to measure technology. But what we can do is use what we know about growth rates to get this growth. So we know that the growth rate of output per effective worker is approximately equal to the growth rate of output per worker, or in real life it would be GDP per capita, minus the growth rate of technology. Here I have kept my approximation sign. Why did I do that? Well, because I know I'm not going to look at steady states where we could write an equal sign. Here I'm really looking for countries that are converging, so that are outside the equilibrium. So any of these growth rates are going to be approximations. So I want to keep it for that reason. I deduced that the growth rate of output per worker is the growth rate of output per effective worker plus the growth rate of technology G. So I can just substitute this expression there and obtain this nice expression for the growth rate of output per worker, which in our case is going to be a proxy for GDP per capita. So what can we know? Well, we know that if output per worker is at steady state, or is output per effective worker is at steady state, then this is 1. So I get 1 minus 1, 0. So I get 1 inside the parenthesis. 1 to the alpha is 1. So I get that this growth rate is going to be equal to G. We already knew that. So that's what I wrote here. And by the way, the growth rate of capital is capital per worker is also going to be G. And since this y tilde t is at the denominator, then I know that if it's bigger than y tilde star, so for some reason a country has more capital and more output than it should have in the long run in terms of effective worker, then the growth rate will be below G. So that's this condition here. And more maybe importantly, if a country is still catching up, so it doesn't have the same level of capital and output per capita as it would have in the long run, then its growth rate is going to be higher than G. All right, so let's now go and look at the data. This has been studied by economists. So we look at whether countries that have lower GDP per capita are converging or not. So here's a version for the United States. So we're looking at regional convergence. This is from Gannon and Schwag in 2015. So here on the left graph, on the x-axis, we have log income per capita in 1940. And what we want to see is whether states that were poorer in 1940 actually had a better growth of income per capita over the subsequent years. So here it's 1940 to 1960, and we're looking at annual log income per capita growth. And so it looks like the theory works very well. So the states that were richer in 1940 actually grew less quickly than the poorer states. Now, they are interested in understanding why this phenomenon looks like it is slowing down. Here we can see the same thing from 1990 to 2010. And it really looks like, yes, there is still convergence, but the negative relation between where some states start and the rate of growth looks weaker and less precise. So they have many explanations in their article, but one observation we can make is that the disparity between states in 1990 was much lower than it was in 1940. So here it's a log income per capita, and you see that it's almost from 8 to 10, whereas here it's centered around between 10 and 10.8. So states looked much more similar in 1990. So it seems logical that they wouldn't have so much to catch up in terms of for lower states. Finally, let's look at the same thing for the European Union. So here on the left graph are the first joiners in the union, and on the right graph are the later joiner. So here, as you can see, it's GDP per capita in 1950, 2005 dollars in log scale. And this is real GDP per capita growth between 1950 and 1980. And again, it really looks like the theory works because the joiners that were poorer back when they joined, like Portugal, Spain, and Cyprus, really got a really great boost by joining the union, whereas those that were already quite rich, like Luxembourg, Great Britain, Sweden, then basically grew at a slower pace. And now what happened to these guys later on? Well, later on, you see that they're mostly all rich, so there's not a lot of leeway to grow even more faster. But all these later joiners, so especially Western Europe, the same phenomenon happened. So they were quite poor when they joined in 1995. And then they became, so they could grow quite fast between 1995 and 2009. So is that it? Is that the theory, or am I claiming a bit too much here? So if you were an economist and I presented you with that evidence, what could you tell me about it? All right. I don't know what you told me. I hope it was a good answer. So what I would say is, well, first of all, there are mechanisms to redistribute wealth within the union, a bit like there are in the United States or Canada or in all unions. So there are mechanisms to make sure that there are not too big disparities between members, but also, and that helped a lot these periphery countries to integrate with the others. But also, one thing that we do have to postulate for the Soros-1 model to predict convergence is that in terms of technology growth, it is the same. So what we're claiming is during that period, there's only one factor that explains this gap between the rate of growth of GDP per capita, and it was capital accumulation. That's the only thing that does change endogenously in this model. However, it's fairly safe to assume that also technology-wise, these countries were not as advanced as as the richer countries in the union, so that G also had a different rate the rate of growth of technology was different between these countries and those countries, and probably that explained it in great deal. So capital accumulation may have played a role, but that I'm not saying that it was the only thing that didn't matter.